Let's discuss an important topic called laminar flow through pipes, or basically flow through pipes. Okay, so here our focus will be to derive the Hagen-Poiseuille equation. Hope I'm right in the spelling. But so we'll derive an Hagen-Poiseuille equation or Hagen-Poiseuille's law, basically equation. Okay, and it's about steady flow in circular pipes. Okay, so let's consider a circular pipe. Okay, and this being the axis of the pipe. Okay, I mean a hollow circular pipe. So let me just draw this. Okay, these are all material. Okay, the solid material. Okay, and flow is taking place in this direction. The cross section is uniform. So let's write what are the basic features of this derivation. The cross section is same throughout, same. So no change in velocity of the flow. This is because from the volume flow rate has to match. Okay, your A1 V1 is A2 V2, and because A1 is equal to A2, so V1 is equal to V2. Okay, so now here we consider the flow to be viscous. Okay, so what we will do is we'll take a cylindrical element, let's say of radius r. Okay, and length is dx. So length is dx, radius r, we take a cylindrical element. Okay, and now we try to represent it, the forces on it. So you have a, so let me just draw that cylinder element here. So because of this you have a pressure. Let's say the pressure exerted by the left fluid is P into area of this, which is PA. A is basically circular because the element is cylindrical element. So its area is pi r square, and here let's say the pressure is varying. So pressure here, let's say it's P plus dou P by dou x into dx. Okay, so how do I'm able to write this? So let's write the new pressure is this into A. Area is same. So now if I assume, now how I have written is this by means of Taylor series. Taylor series basically gives you, if I know the pressure at P of x, I can find out the pressure at P of x plus h. So P of x plus h is P of x plus h into dou P by dou x or dP by dx plus h square by 2 factorial into d square P by dx square, and so on. So what we do is, if I assume h to be delta x, so all the second order terms can be neglected because delta x whole square is something which I don't want. So P of x plus delta x is P of x plus delta x into dP by dx. So this is the new pressure, I mean the pressure at a distance x plus delta x, and this is the pressure at x. So this is what is this P of x, and this term is what is this. So dou P by dou x, dP by dx I have written just dou P by dou x, and delta x I'm writing dx. So this is what is the pressure at x plus delta x. This is the pressure at x, and this is the change in pressure. So if I know the pressure at x, I can just express pressure at x plus delta x in terms by means of this equation. Okay, and now I have viscous, because the flow is viscous, so the top fluid and the bottom fluid will try to resist the motion of this, and obviously the velocity here will be 0 because of the no slip condition, and velocity will be more towards the center. So as the center travels with more velocity, center part of the fluid travels with more velocity, so the top fluid will resist towards left, and let's say the shear stress is tau into the lateral area, which is 2 pi r, into the length is dx. So this is what is the forces. These are the forces. So A is basically the pi r square. Remember, we have taken cylindrical element of radius r. Okay, so A is pi r square. So if I balance the forces, the sum of all the forces has to be 0 because there is no acceleration. I mean, I assume that Ax is 0. It's a steady and uniform flow. So if you assume, I mean, if you from kinematics, if you recall what is Ax, it's dou u by dou t plus dou u by dou x u plus, so as the flow is, okay, let's write down dou u by dou y v plus dou u by dou w dou u by dou z w. As the flow is 1D, so these terms will linear will 0, and I don't assume that, I assume that u is constant, that is the horizontal velocity component of the velocity is constant, so this is also 0, and the flow is steady. So because of the steady, this term is 0, and because of the uniform flow, u is constant, so dou u by dou x is 0. So I get Ax 0. So when I apply the Newton's law, delta Fx is 0. So the way I apply is the total pressure is P into A, rightward pressure. So I get P into pi r square, then minus P plus dou P by dou L, let's me write dx into d into delta x pi r square. Okay, or let's continue with our same thing, dou P by dou x into dx pi r square, and then tau is resisting, so 2 pi r dx is 0. So this is the equation. P pi r square comes cancel, so when I rearrange, I get minus dou P by dou x dx pi r square is minus 2 pi r dr equal to 0, or tau is basically minus dou P by dou x into r by 2. So this is one equation. From this I can see that at a section, at a cross section, when r is 0, tau is 0, and when r is capital R, tau has some value which is tau naught minus 2p by dou x into r by 2. So it varies, you can say that it varies linearly from being from 0 at the center to tau naught at r. So this is the variation of shear stress in a circular pipe with uniform flow. So now let's try to derive how the so this is what we got, an equation between shear stress and the pressure variation. Let's now try to derive more about the an equation of the velocity distribution, and from there how a flow rate will be affected in terms of how is the pressure loss and how the velocity distribution is related. So let's now apply the Bernoulli equation. Remember this is a real fluid, so we need to consider the head loss. So the pressure terms at the section is, these are the terms, height is same, so z1, and apart from the regular terms, we have the head loss due to viscosity. Okay, so now v1 is equal to v2 from continuity we got, and z1 is equal to z2 because it's at the same level. So what we get is p1 minus p2 rho g is the head loss. So this is another, so as obviously the pressure should decrease from the previous analysis, what we have seen, the pressure should decrease in order to the dou p by dou x is negative, it should decrease to balance the shear, to balance the fluid friction. Okay, so that is almost clear from the force balance. So now let's convert. So this is one equation which will later use it, but now let's again, we have got tau as minus dou p by dou x into r by 2. So this was the first equation. Now let's express Newtonian law of viscosity. Now Newtonian law of viscosity, let's apply. It says that from a surface which is fixed, your shear stress by Newton's law of viscosity is expressed as this, we have seen in the beginning chapters, is expressed as tau is minus mu, or sorry, the shear stress is mu dou v by dou y, where y is the distance from the wall surface. Now my r, small r, is I'm measuring from here, and this is my total r. So y can be written as, because this formula is derived from the fixed surface, so y I can write as small r, capital R minus small r, and so I can write that dy is minus dr because r is constant. So this expression can be written as minus dou v by, so I mean, if you want to write in a flat way, so dou v by dou y can be written as dou v by dou r into dr by dy, and dr by dy is minus 1, so minus mu dou v by dou r. So this is when I apply Newton's law of viscosity to this circular piece. So this is shear stress. So if I equate these two, what I get is minus mu dou b by dou r is minus dou p by dou x r by 2, or dou v by dou r is 1 by 2 mu dou p by dou x into r. Okay, so now I need to integrate this. So integrating this 1 by 2 mu. So dou p by dou x, I assume that dou p by dou x is not varying with r. It's varying with, the pressure drop is varying with x, but it's not varying with r. So this becomes r square by 2 plus constant. Okay, so this is how I get an equation. Okay, so this can be now rearranged into, so this is a constant. So what I know is that how I can eliminate constant is that at r is equal to capital R, at the surface of the solid, velocity is 0. So from this I can get that 1 by 4 mu dou p by dou x is capital R square is c, and if I substitute that constant here, I can add velocity to be 1 by 4 mu dou p by dou x, and I can write small r square minus capital R square. So this can be rearranged to be 1 by 4 mu minus dou p by dou x into capital R square minus small square. So this is a general expression for the velocity. So what does this tells us? This tells us that the velocity distribution is parabolic. Okay, so if I happen to plot a velocity distribution, at the center line the velocity at r is equal to 0 is maximum, and at r is equal to capital R is 0. That is so it varies something like this. This is how velocity varies. It's this is the distribution of velocity with radius. It doesn't vary with x. That is what we have assumed in deriving this, because the area of cross section is constant, but it varies with r. So this is your velocity distribution. And the shear stress distribution is, it's 0 at the center that we have seen, and it is tau naught at the wall surface. So shear stress is 0 at the center and it's tau naught at the wall surface. So these are your velocity distribution and the shear stress distribution. Now let's, from the velocity, now let's see how your flow rate can be related to the head loss. Okay, so what we got is 1 by 4 mu. So remember, mu is your dynamic viscosity. Okay, so Vmax is at R is equal to 0. So when I substitute R is equal to 0, I get Vmax, which is 1 by 4 mu minus dou p by dou x. Dou p by dou x has to be negative. That's why the minus of that will give you positive. So this is Vmax, maximum velocity occurring at the center line, occurring at the center of the pipe. Okay, so now I need to find out the volume flow rate. How do I find the volume flow rate? If you recall, we have taken cylindrical element, so the flow rate through that cylindrical element would be V into 2 pi r. Okay, now let's find out the let's talk about flow rate, how to calculate flow rate. So in the cross section of the pipe, you have the cross section of the pipe like this, and let's say you have at r, you have, this is the thickness is dr. Okay, at a distance r you have this velocity v. So this area I am calling it to be small dA. So v into dA is the volume flow rate through this small ring element. V is the velocity at a distance r, so we have taken a distance r, and dA ring element can be written as 2 pi r into dr. This is dq, and if I add all such ring elements throughout the circumference, throughout the cross section, I get the total volume flow. So V 2 pi r dr, and V is basically, so V can be expressed in terms of your, okay, so 1 by 4 mu, let me just write down entire thing, minus 2 pi by dou x r square minus small r square into your 2 pi r dr. So this I need to integrate from 0 to capital R. So once I integrate this, you will observe that I okay, 1 by, let's do it, 1 by 2 pi mu, okay, minus dou p by dou x is constant. So once let me integrate, so r square minus r square into r dr. So these terms will be your r square r minus r cube, and when I integrate these terms, what I get is minus pi by 2 mu dou p by dou x. R square, if you integrate, it will be r square by 2 minus r power 4 by 4, and when I substitute the top integral, so I get pi by minus 2 mu dou p by dou x. This is r square by 2 minus r power 4, so r power 4 here by 4, and the zeros will be 0. So this becomes r power 4 by 4 inside the integral, and finally I get pi by 8 mu minus 2p by dou x into r power 4. So this is the general expression for volume flow rate. And how I define, now these are two important concepts. Now V mean is basically, you take the total flow rate divided by the total area of cross section. That is, when I take Q by is pi capital R square is the total area of cross section, I get pi by 8 mu minus dou p by dou x, and because this is r power 4, so pi is r power 4, and when I divide by pi r square, I get minus dou p by dou x 1 by 8 mu into r square. So if you compare this Vmax and this V mean, what we will see is that V mean is half of Vmax. So this is one again important things. Most of the time a question comes in GATE where the mean velocity in a circular pipe is given and maximum velocity is asked. So you can just relate in this. Remember, this holds for a circular pipe only. Okay, so now most of the time, because you know the volume flow rate, so it's always it's better to express everything in terms of mean velocity. Okay, so now let's again go back and express our entire head loss. Remember, our objective, we have derived small derivations, but our main objective in this is to derive the head loss expression. So that is what we are going to derive. So we got V mean as 1 by 8 mu minus 2p by dou x into r square. So let me write this. So V mean, from now onwards V mean I'll consider as total V, capital V, that is the mean velocity, and so minus 2p by dou x can be written as 8 mu V by r square. R square, if I express in terms of diameter, will come d by 2 whole square, which will be 32 mu V by d square. So this is minus 2p by dou x. Now if you remember, we have derived, so this thing is now constant, right? Now you remember that the pressure gradient is constant, it's not varying with x. So I can just take, instead of taking a smaller section, whatever the pressure gradient, it's not changing with x, it's a constant. So I can write this to be p1 minus p2 by length of the pipe, because it's constant. So it's p2 minus p1, and because of this minus I can write p1 minus p2 is 32 mu v by d square. Now p1 minus p2 we have already derived from Bernoulli's in the previous some steps before, is this p1 minus p2 by rho g is the head loss. So p1 minus p2 I will write rho g hf by L, which is 32 mu v by d square, and hf can be written as 32 mu vl by rho g d square. So this is a general expression for the head loss in a pipe, 32 mu vl by d square by rho 32 mu vl by d square. So this is the head loss, pressure head loss. Okay, and in terms of pressure you can write p1 minus p2 is the pressure drop. So hf can be written as p1 minus p2 rho g, and that is 32 mu vl by d square rho g. So the pressure drop is p1 minus p2 is 32 mu vl by d square. So this is another important relation for pressure drop. So now we always express this in terms of q. I mean the pressure drop we always express in terms of q. So that also can be written, because you know that q is what, area of cross section into v, and area of cross section is pi d square by 4 into v. So if I express my v in terms of q in this expression, so I'll get p1 minus p2 is 32 mu l by d square, and v as q by pi d square by 4, which is 4q. So this becomes 128 mu l q by pi d power 4 is my pressure drop. So this is the so-called your Huygens-Pauli equation, or the other way of saying is q is p1 minus p2 pi d power 4 by 128 mu l. So this is the so-called Heisler-Pauli equation, which expresses, so in a pipe, if I have the pressure drop, say p1 p2 is the pressure, p1 minus p2 is the pressure drop, then the volume of flow rate, the amount of flow that I can pass through depends on the pressure drop and the other geometry parameters, and more importantly on the value of this viscosity. So higher the viscosity, lesser is the volume flow rate which I can pass for a given pressure drop, or for a, I mean it's all dependent on this. So it's something like, if I want to compare, this is q, this is the pressure drop, is the voltage, and the entire thing is the resistance. So this is like your current, you're passing current, your resistance, and the voltage drop is the pressure drop. So this is like your voltage drop, this is like current, this is like voltage drop, and this is like your fluid resistance. So your R is 128 mu L by pi d power 4. So this is like your resistance offered by the pipe. So I can compare this with like the Ohm's law. So higher the voltage drop, I mean for a given voltage drop, higher the resistance, I can pass lower currents or lower flow rates. So this is what is the physical meaning of Heisenberg equation. So now let's summarize. So the summary for all this is that for a steady uniform flow that is constant diameter, okay, the head loss HF is basically your P1 minus P2 by rho g, which is your 128 mu QL by pi rho g d power 4. So I have just expressed everything in terms of head loss and Q. So this is the general equation, and your velocity mean, which is the total discharge by area, is half of Vmax, and your distribution can be written as V to Vmax into 1 minus R square by capital R. So these are some general equations. This is the basic Heisenberg equation which relates the head loss due to occurring due pressure with the volume flow rate. This is the comes from the velocity distribution. How is the mean velocity related to the max velocity, and this is the velocity distribution for a steady uniform flow. Now another thing is that most of the time in the flow through pipes we also use the Darcy-Weisbach equation that can be derived from this, and let's derive that. HF is 128 mu QL by pi rho g d power 4. So if I happen to express this in terms of my velocity, we also written this in terms of velocity some time back. So that was 32 mu v L by d square. So if I express by rho g, yeah, this what, if you express q again in mean velocity and area, you will get this. So now 32, so let's separate LV by GD. So I'll get something called 32 mu by rho d here, and I'm trying to express this in terms of a Reynolds number, which is for a pipe is rho v d by mu. So okay, so if I substitute for rho d Reynolds number, I get 32 rho d. So rho d by mu can be written as Re. Rho d by mu can be written as Re by V, which I write here is Re by V LV by GD, and this will become 32 LV square by GD by Re. So most of the time we write here LV square by 2 GD and into 2 multiply, so we get 64 by Re LV square by 2 GD, and we call this as the Darcy friction factor, that is the friction factor, and we express the other term as LV square by 2 GD. So this is the head loss, and this equation also we use in pipes. This becomes your Darcy-Weisbach equation. Okay, and this term, that is 64 by Re, is called the friction factor. So most of the time if the friction factor is given, you can directly express in these terms, or we have already shown that for this we have derived from basics, and we have shown that this is nothing but this can be expressed in the head loss for laminar flow can be expressed in this way, provided that friction factor becomes 64 by Re. So there is another way of representing. So we have seen Heisenberg equation and how it can be viewed as a Darcy-Weisbach equation, provided you call the friction factor as 64 by Re. So this is all about losses, flow in pipes, flow in circular pipes. Next we'll see what is major loss and minor loss. In fact, whatever we have derived is a major loss which is occurring due to friction, and so we'll categorize that.